Before we start solving a problem, it's important to review some of the basic rules to prepare and form Lewis structures. This slide refers to the octet rule exceptions. We can think about three types of exceptions. The first one refers to when we have electron deficient atoms such as boron and beryllium. As we can see in this example, beryllium chloride has beryllium as the center atom, and this atom does not have an octet rule. We have simply two single bonds, that is 4 electrons. Another example of electron deficient is boron trifluoride, in which boron is the central atom. Here we have only 6 electrons defined by each of the single bonds. The other type of octet rule exceptions refers to free radicals, in which we have an odd number of electrons, which makes it impossible to have 8 electrons surrounding an atom. In this example, the octet rule is violated in regards to the nitrogen, the central atom, that has 3 single bonds, that is 6 electrons, and 1 electron, lone electron, so that's 7 electrons. And this one has a resonance structure in which the lone electron is localized in oxygen. In this situation, the oxygen does not meet the octet rule. We have 1 bond, and then we have 2 lone pairs, so that's 6 electrons, and 1 single electron, that's 7 electrons. The third type of exception to the octet rule is for nonmetals from period 3 or higher that have an expanded valence shell. And this is possible because there are available d orbitals that participate in bonding. 2 examples that we have here is phosphorus pentachloride, in which the central atom phosphorus has 5 bonds, that is 10 electrons, 2 more than the octet rule allows for. The other example is sulfuric acid, H2SO4. The central atom of interest here is sulfur. This has also an expanded valence shell. We can see that it has 1, 2, 3, 4, 5, 6, that is 12 electron pairs. Indeed, this is higher than the octet rule allows for. So now, with this background, let's move on to solve a problem in which this concept needs to be applied. The problem reads, there are 3 species below, and they do not obey the octet rule. Draw a Lewis structure for each of these structures and state the octet rule exception. So take a few minutes to think about this problem, propose a solution, work the solution, and after that let's compare our answers. The plan to solve this problem will consist of first counting the valence, bonding, and non-bonding electrons of each of these structures, draw the corresponding Lewis structures, and finally identify the atoms in which the octet rule is not met. Let's solve first O3 minus. So we're going to draw the Lewis structure for this compound or this species. So that means that we're going to have 3 oxygen atoms linked by a single bond. Let's count the valence electrons. So for valence electrons, we have 6 per oxygen times 3 oxygen atoms equal 18 electrons, plus 1, because this has a negative charge, is 19 electrons. Then the bonding electrons are going to be 2 per bond times 2 bonds equals 4 electrons. The non-bonding electrons is going to be 19 minus 4, which is 15 electrons. So what we need to do is place those 15 electrons around the several atoms until we meet the octet rule in as many atoms as possible. So let's begin by placing 6 electrons on the first oxygen, 4 electrons on the middle oxygen, that's 10 electrons, and we have 5 more. 1, 2, 3, 4, 5. As we can see here, this oxygen does not meet the octet rule. So this is basically an exception in which we have a radical exception. It's important to keep in mind that this species has a negative charge. So we put it in brackets and put a negative charge. And that if one wants, one can also draw additional resonance structures for this one. So let's add that. So the idea is we have to find other structures in which we are going to localize the lone electron onto other atoms while the bonds are not disturbed. We use the double-headed arrow to indicate the resonance structure, and we can imagine that we can take one of these electrons, for instance this one, and pass it to this structure over here. So the other resonance structure will be fairly similar. The bonds remain the same. The lone pair of electrons remain the same on the first oxygen. This one now has only one electron, and this one has 6 electrons. So now this is the radical, the electron that causes this to be a radical. The third resonance structure will be similar, but we can actually take one of the electrons of the first oxygen to here, and we can easily see that now the radical results from having a lone electron in the first oxygen right here, F2. The Lewis structure for that will assume that xenon is the central atom, and fluorine atoms are going to be connected to that central atom. So the valence electrons that we have here, we have 2 fluorine atoms times 7 electrons plus 8 electrons for xenon. We have a total of 22 electrons. Bonding electrons, we have 2 bonds, so 2 electrons per bond times 2 equals 4 electrons. Non-bonding, (22 minus 4), that is going to be 18 electrons. If we place those 18 electrons on each of the atoms to try to meet the octet rule, we have 6 on one fluorine, 6 on the other fluorine, that's 12. We have 6 more, and these 6 more electrons will have to go onto the xenon atom. It is clear from here that xenon has an expanded valence shell. For BF2, we have one central atom, beryllium, and 2 atoms connected to beryllium, 2 fluorine atoms connected to beryllium. So the valence electrons will be 2 fluorine atoms times 7 electrons each, plus 2 electrons for beryllium equals 16 electrons. Bonding electrons, we have 2 bonds, 2 electrons per bond, 4 electrons. Non-bonding, (16 minus 4), that's 12 electrons. We position those 16 electrons on the various atoms, beginning with the most electronegative ones. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Fluorine meets the octet rule for both atoms, and there are no more electrons to place on beryllium. The exception to the rule is beryllium that has an electron deficient shell.